It's a pleasure to introduce our third speaker this morning, Omer Reingold from Stanford, and he'll speak on applications of pseudorandomness to pseudorandomness.
Yes, so that's the revised title. The reason, it's kind of the title of the workshop implied something about applications or something, or usefulness of pseudorandomness, and that's the best I could find is data structures. But actually, one point is that it kind of, the pseudorandomness in the data structure applications that I have is kind of very thinly disguised. So the questions are questions of explicit constructions. So that's one reason. The other reason for the title is that, as we'll see, so I could have titled it something like from pseudorandomness to data structures and back again, or something like that, because many of the applications from the data structures got into kind of harder core pseudorandomness and back. So that was my talk, and I hope you... Okay, so I'll try to talk about part of a body of work, starting with this work with Celis, Regev, and Wieder on load balancing. So hash functions that are good for what's known as balls and beans applications, kind of load balancing. And that would imply, or did imply, various kind of other works. One is a work that showed how to efficiently construct log n-wise independence and epsilon bias sequences, where efficiency is the number of word operations, and that in turn came back to improve the result for load balancing. Together, these two works allowed us, with the work with Rothbaum and Wieder, to do hash functions for more sophisticated applications of data structures like cuckoo hashing to choice, which very recently was extended to k-choice. And also, this entire approach kind of gave rise to pseudorandomness for restricted forms of small memory computation. With the first work was Gopalan, Meka, Trevisan, and Vadan. And I think that Thomas Stinker would talk about some of the later applications of that. But I think that with all of this work, there are still lots of very, very clean open problems on data structure that are both well motivated and seem within reach, which is probably the main reason I'm kind of giving this talk. So let's start. So data structures, which are, of course, structures that hold data. Yeah, the entire talk will be like that. But we'll focus on dictionaries, which is a structure that holds one of the simplest form of data, which is just a set. So you have a set S, which, without loss of generality, usually we can think of it as a set of the, let's say, numbers 1 to n cubed, and it's of size n. And of course, we don't know what set, so our data structure should work for any set. And we look at very basic operations like the insert time, lookup, and of course the memory that's needed. So insert is how much time it takes to insert a new element into the data structure. Lookup, how much time it takes to figure out if an element is in the set or not. And the memory is what we're trying to optimize, or another thing we want to optimize, which is how much memory it takes to hold this set. Ideally, it will be just something close to n words of logarithmic length. So kind of for example, we can hold it just as a sequence of names, the first element, the second element, but then lookup will be long, and we'll be looking at more sophisticated structures. And for all of these, or for all of the dictionaries that we will look at, all of them are using these kind of hash functions. So the family of hash functions from a universe U to the target T, where U is just this n cubed, and T is of size n. T is just, we want to hash selecting H from H, and we're hashing our set into this kind of smaller domain, which is the domain of the ideal size. So ideally, if this hash function will send every element to a different location, then it will be very easy for us to implement our data structure. Here is S. So ideally, we'll just select H from H and hash every element to its location, store it in its location, and if there are no collisions, it's very easy to insert. You just evaluate this hash function once, and to look up, you evaluate, see if the element is what you expected it, and everything is good. But functions from n cubed to n elements can't avoid having collisions. That's unavoidable. So if these are hash functions, what's used for all of these data structures?
Can you explain why it's n to the 3?
Why can I assume that the universe is n to the 3 and not larger?
Why n to the 3?
Yeah. So sure. Exactly. Russell. So it's pretty easy to store, to hash. If we're using hash from a bigger domain to this domain. So originally our domain may be larger, but if we hash it to a domain of size n cubed, we don't expect any collisions. The birthday paradox would die around n squared, and with n cubed, with high probability, we don't expect to have any collisions. So with something that's pairwise independent or close to pairwise independent, we can hash our original set into this kind of a domain. And now the problem is that when we want to continue this kind of happy procedure and to hash all the way to what we want, we are faced with collisions. And so instead of hash functions, what we actually will use is hash tables. And let me do a very, very brief crash course on data on hash tables, which will include everything that we will care about in this talk, and probably almost everything I know about hash tables. So it will be we will be in the same level at the end of the next few words. Okay, good. So one thing that we can do is something called open addressing. Which is very natural. After we hash into this array of n elements, we have some collisions. So wherever we have a collision, we will create this kind of a list. So what would be the insert and the insert time and the lookup time in that situation? So the size of the memory will not be much larger than what we want. It will be order n. Actually, the constant will matter eventually, but let's ignore it for now. But the lookup time and the insert time, in the worst case, and for an average there will be constant, but in the worst, for a worse element, for some of the insert and lookup, it will be as long as the longest kind of chain, as the longest collision that we have here, which will be, for a random function, essentially logarithmic. So it will be log n over log n. That's the length, the largest length we expect. So insert and lookup or log n. Another thing we can do is linear probing. And here what we're going to do, we're hashing an element, and this location is occupied. And also the next location is occupied. But the next one is not occupied. So instead of inserting the element here, we're going to insert it to the first empty location. What would be the insert and lookup here?
Can't be better than the previous one.
It will be exactly the same one. So it will be log n and log n, because as long as your array is a little bit larger than n, you don't expect, so it's 1 plus alpha n, you don't expect any kind of segment to be longer, occupied segment to be longer than logarithmic. So that's one other thing you can do. And now we get to two things that are a bit more sophisticated, and these are the two applications that will eventually reach over here, kind of the cuckoo hashing and two choice. So with cuckoo hashing, instead of one hash function, we're going to have two hash functions. We're going to have two arrays. One alpha n. We have, so an element x is mapped by g to a particular location and by h to a different location. And now we're going to insert our element in one of these locations. So lookup is going to be constant. We just need to look at two locations. But what happens if a location is already occupied? Then we start moving things around. So this element is already occupied, let's say both of them. Then I'm going to move this one to the next position that's possible. And then the other position is occupied, so I'll move the element that's there to its other position. And hopefully this will terminate and terminate quickly. And essentially, insert time again will be, in all of these, it will be order 1 on average and logarithmic in the worst case. So the longest you need to do this kind of changing the positions will be logarithmic. At the face of a question.
When you change, you mean change to the other list, but to the other function?
So you put here, and here there is y. So we'll move y to the position g of y, because y can be also in this position. But here there was z, so z will move to age of z. So each one has two locations, and we'll start moving them around. And the power of two choice will do something very, very similar, but for open addressing. So this is, I mean, I'll almost not talk about it later, but this is kind of a remarkable result that probably most of you know, but if you don't, this by itself is worth the talk. And the power of 2 choice says that if you hash, let's say you hash this set with 2 hash functions, age and g. And every element in its turn, you look at the 2 locations that it can be, age and g. And now let's say that you select the location that's less occupied, right? So in this situation, right here, the largest load would be log n log n, sorry, log n over log n. And here, when you do this process, which depends on the order, but regardless of the order, then the heaviest bucket, the heaviest location, will have log n elements. This is quite remarkable.
So I just want to understand the difference. So for cuckoo hashing, what is the difference with cuckoo hashing? For cuckoo, you look at the one. If it's open, you do it. You look at the other. If it's open, you do it. If not, you move the second one.
Right. So here you just add it to the location. So it's like the open addressing. Or you can just think about it in terms of hashing. I have these balls and bins. So this hashing, we usually call it kind of balls and bins. The elements of S are the balls, and we're throwing them using age to the bins here. Now the question is, what's the heaviest bin? How many elements are in the heaviest bins? So just thinking about it this way, when you're throwing them, but at each point you look at 2 locations, and you throw it to the one that has less balls, the number of balls in every bin will drop exponentially to be log. And now you can do open addressing here as well, right? So you can do open addressing, and whenever, because there will still be collisions, you just have a chain. So these are all the data structures that we're going to talk about. So if there are questions here, it's a good.
So the advantage of cuckoo hashing is that lookup is constant worst case.
Right. So yeah. So here, lookup and insert will be log. But it's still kind of the length of the largest chain.
You just keep a counter how many elements are in each cell and insert.
Yeah, you can. Right.
No, but
you can insert. Right. You can insert actually. Yeah. You can. Yeah. It depends on exactly what. Yeah. But.
Okay. Sort of just to understand your quantifications, you have a sequence of inserts, right? So you'd like us to think that they are oblivious to the selection of
right. So most things here.
Adaptive.
Right. Most things work in an adaptive setting where you're inserting elements and then taking them out and inserting. But here, for this talk, let's just think about a completely static thing. So the entire sequence of elements that you're going to insert are fixed in advance. Definitely, you don't want the elements that you insert to depend on the hash function.
This is what I asked.
That's definitely not. But what you can do is have inserts and removals and inserts. But you are right that with the right implementation, inserts in all of these is order 1, but the lookup is right, because you can always insert at the beginning, not at the end.
Well,
I mean, it depends on exactly what's the
Yeah, the depends if your problem is that the insertions will all be distinct. Like normally you want.
Right.
Normally you want to check.
Right, that's true.
Normally, so insert contains lookup because you don't want to.
That's true. Okay, so that's the level of data structures that we were not going to. But you're all right. Yes.
So previously, I kind of thought of hashing in the sense of pseudorandomness as like it has some property in its name, like ky. So it fools an adversary that looks at k random variables at a time or something. Does this fit into that framework too, or like where does pseudorandomness kind of?
So these are all okay. So let's talk about it. Thank you. So what do we do in data structures. So we said, okay, these are the functions, and so what we usually do when we start analyzing these data structures, we assume that the hash functions, all these hash functions are totally uniform, right? And in addition, when we analyze, we think that storing them comes for free. They just exist somewhere for us, like a random oracle. And every time you evaluate the function in a location, it takes order 1. So it's just one operation. So this kind of an ideal situation is the one in which we analyze all of those. But now we can start asking the usual questions that we care about in a pseudorandomness workshop, which is explicit functions. Can we get the same properties with explicit functions? This is a line of work that started a long time ago. I think definitely from Carter and Wegman, you can think about their work in this, or when they thought about their work in this setup of data structures. In practice, the problem is solved because usually you can just use a cryptographic hash function, which we already kind of assume that they have these perfect scenarios, perfect randomness, even after we find out that they don't. But probably for these applications, it's absolutely fine. But it won't stop us, and there's lots of great work in this domain, very beautiful pseudorandomness work, and that's what we care about. So here you have constructions, you have proofs, and you want to fool these proofs. You want hash functions that fool this proof, and I think by now I kind of completely provided my duties to the name of the workshop. Right? We're going to fool the proof that all of these things work. But yeah, the kind of things that we're going to use, the building blocks, are exactly the building blocks that you've been talking about. So all of these nice functions that we really like k-wise independence. So let me just define it, although I probably don't need this audience, but this is essentially the only, everything here is going to be very elementary. And this is the main object that we're going to use is k-wise delta dependent hashing. So we said random functions work, but we want something that will use much less randomness. And actually, what we'll see is that although we came to look for small description length, so small family of hash functions, the main advantage of what we came up with was better efficiency. So we'll also care about the efficiency of our functions. But k-wise, delta dependent hashing. So we want our collection H. Family of functions from. Such that for every k distinct inputs, the value of the function looks like it's random. So the function behaves almost like a random function when you restrict it to just k inputs. So for every collection age of x1 up to age of xk, where age is selected uniformly from this family age, so these are random variables, there are delta close, so close up to statistical distance delta, L1 distance delta, from kind of the uniform distribution over T to the K. And K independent outputs.
Do you care about k at most like log n because of this maximum bin size? Is it the right intuition?
Right. So again, the next thing I'm going to say is that for all of these creatures, log n-wise independence work. So that's what we're fighting against. So another possible title for the talk is de-randomizing log n-wise independence. So all of these creatures work with log n-wise independence or log n-wise 1 over poly dependent functions. Some of them, at least when you only care about expectation, you can do with less. So for example, linear probing, one famous result is that I think 5-wise independence work. But we want our hash functions to succeed with high probability, and with high probability from now on for this talk will be with probability 1 minus 1 over poly, so 1 minus 1 over n. You want the failing probability to be 1 over n, or any polynomial in 1 over n. So log n-wise independence works for all of these constructions. And that's essentially kind of the common de-randomization. Eventually, when we talk at the end, in one open problem, so some of the open problems exist in a setting where we don't even know that log n-wise independence work. So for example, for a cuckoo hashing, or something called blocked cuckoo hashing that I'll mention later, hopefully, we don't even know that log n-wise independence work, and our functions won't work as well. So that would be one open problem. Okay. So what do you get? What do you get from log n-wise independence? So let's look at seed length and evaluation time. And evaluation time, let me say something about it. What do we mean? What's the model that tells us evaluation time? This is the common model is the word RAM model. So you're allowed random access, and in addition, you're counting word operations. So if, and a word will consider, let's say, any one of these blocks is a word. A word will be of logarithmic size. We're asking how many operations like that. As far as I know, I don't know, correct me if not, but it's not a very well-defined model, because the question is what operations are allowed. We only want to allow simple operations, and we'll only have kind of simple arithmetic operations. But it's still a good question of what exactly it means, but I think that what we give does fall in that realm. But you don't want, for example, to allow exponentiation. So g to the I for a large I shouldn't be order 1 operations. Yes, Russell?
So you could like view any function on epsilon log n bits as constant time, because you could make up a table. So any function that's kind of decomposed.
Right, but then you'll pay with the seed length. So actually, yeah, so what I want is, so perhaps seed length is not necessarily the right way to think about it. You should think about what do you need to write to describe. So description length. Call it description length. So if to get order 1 evaluation, your description should contain a table, then in the description length you should write the length of the table.
Okay. But I mean, if you're using the same table for every function, then I wouldn't count it as a description.
Sure.
So if you're doing like addition or multiplication, and you can break it down into epsilon log n bit strings, and you have a table that helps you evaluate it.
Right. But then what's the length of this table? So, okay, so you're saying there is some table in the world, so perhaps. Okay. But we're here now kind of in a standalone kind of setup, where you just have one hash function and you care about how much did it take to describe it and how much was the evaluation time. You're right that potentially you can reuse some things from one to the other. Okay, so let's talk about kind of log n-wise independence. The standard implementation of log n-wise independence are degree log n polynomials, right? So a hash function is described by a random degree log n polynomial, and you evaluate it at any given point. So the description length are, you have log n elements in the field. So the description length in bits will be log squared n. And the number of the evaluation time will be order log n. So we're counting description in bits and counting evaluation in words, operations, but you can call it log n. That will be consistent.
Omer, just like a question, just to make sure. In textbook, usually after in introduction, there is a chapter on perfect hashing. So what's wrong with perfect hashing? Is it data dependent thing or?
Perfect hashing, well, okay. So, so it's a chapter, and we don't have time for another chapter. But in chapter, so you usually need the entire set. Here we're getting the set one by one, and
so kind of
you're not allowed to process something for the entire set. I mean, regardless of. So you're perhaps there are even better answers, but that's mine.
So Omer, this is description length and evaluation time for doing what? K-wise independence?
Log n-wise independence. So if you implement age and g as log n-wise independence, then describing age will take log squared n bits, and evaluating will take log n operations. Now, that's not the only way to implement log n-wise independence. There is a very beautiful work of Siegel that have description length order n to the epsilon and evaluation order 1. So that's Siegel. And he also has a lower bound for log n-wise independence, where if you want to get below log n, essentially you need to get to very high description length. Still in practice, and there's a line of work following Siegel with simpler and more efficient applications of this, really very nice line of work. And in practice, this may be a good solution, probably a better solution than that one, because anyway we're storing n words, so perhaps it's okay to store n to the epsilon more. So you kind of chunk it into the data structure.
What is the dependence on epsilon? Is it an order of 1? It's like 1 over epsilon squared or something?
It's a decent dependence. It's not crazy. I mean, yeah, I don't remember if it's 1 over epsilon or squared or something. I think probably, yeah, I don't know. Now, what would be the dream version? The dream version will take order log n. Now, this I know that it's possible. And I'll argue later that it's possible because the entire thing is an instance of, or at least for balls and beans, because the entire thing is a special case of space-bounded computation, and we know that there is a generator of space-bounded computation with seedlings log.
You're talking about exact still or approximate? With the delta or?
So that's okay. So that's about applications with log n-wise independence. So if you try to solve these problems with log n-wise independence, that's the two extreme things that we know. And essentially, and we also know by the work of Siegel, a lower bound, that this is necessary. There's nothing better than that. This is optimal in the two cases. Okay? But our problem is not to construct log n-wise independence. Our problem is, for example, load balancing. So there we can hope for something better. So here I'm asking, what can you do with less bits? And the dream thing will be order log n and order 1. That I know that it's possible. this, I was quite surprised, and I think others were quite surprised that we made progress also in evaluation. Our goal was to get closer to this, but we actually did better in terms of evaluation. And what we can show here is order of log n, log n, and order of log n squared. That's what we can show. I was really upset with the organizer that they allocated an hour. I thought, oh, I need to prepare so much stuff. But yeah, but no. Okay, good.
So you can do that both for balls and beans and for power of 2 choice?
For all of those, we can do that. With these two cases, we don't get the best constants. And the constants matter. So what's the size of the data set? And this is a great question. And there are questions in terms of the pseudorandom objects that we build that directly would give us what we need. But we solve all of those with these parameters.
So in the truly random function setting, if the size of the table is 1 plus alpha times n, then say in the power of 2 choice, the longest list will be order of log n with the constant dependent on alpha. Is that how it works?
No, here you just need n.
Oh, just n.
And it will be log n plus order 1. Not even
1
order.
times log n. Yeah.
1 times log n plus order 1. And you can get even constants that are smaller by looking at k choice. If you have k functions for some constant, you decrease the constant. It's quite amazing. Of course, the main advantage you get already from 2. Because you drop from log n to log n, and then you can reduce the constant with seeing more. It's an amazing result. Yeah.
So when you say you don't get the right constant, is that you need the table to be of size more than 1 times n, or that more than 1 times log n?
Yeah, so the question is how many, so our table will be larger by some constant than what it should be. And here, okay, so if we'll get there, I'll get to the. Okay, so let's talk about the balls and beans. I wanted to tell you why log n wise independence work. Let me kind of just hand wave it. Log n wise independence work just because we can use a union bound over all possible sets of size log n. So if we consider a particular set S prime, which is small, it's of size log n, let's say, or log n over log n, and we ask what's the probability that this entire set is mapped to a particular location, to a particular bin. This is going to be small. It's 1 over n to the size of the set, 1 over n to the log n over log n, and this is enough to kill the number of subset of S of this size. So it's a very kind of trivial brute force argument, and this argument only used the randomness for sets that are small, of size log n over log n. So you don't need full randomness, it's enough to have log n over log n wise independence. From now on, let's call it log n wise independence. Yeah. What about pairwise independence? Okay, log n wise independence work, but pairwise independence is very powerful. Can we do with that? No, not in general. So there is a lower bound of Alon et al. That show that pairwise independence in the worst case. So perhaps there is a pairwise independent functions that are good, or surely there are pairwise independent functions that are good, but not every pairwise independent functions would be good. The size of the largest bin, depending on the level of independence, will be polynomial. Instead of logarithmic, it will be n to the epsilon. That's square root n. Okay.
Was
Yeah, square root of n. And I think it can be extended to order one-wise independence and so on. So that won't work. What Alon et al. Also showed is that random linear mappings do work. So random linear mapping, if you take over Z2, so if you take a random matrix and you use it as your hash function, it will produce bins that are at most log n times log n. Which again, it's a very beautiful result. It doesn't help us because although these are pairwise independent, this requires still log squared n bits. So it won't give us an improvement in the description length. So a particular kind of pairwise independence that has very large description length does work. So what do we do here? We construct. So what we observe, is that pairwise independence doesn't work in general, but it can bring us some of the way. And then we can continue with four-wise independence. And we can continue then with eight-wise independence. So we can make gradual progress with increasing level of independence. And we only need the log n-wise independence at the end. So how would our functions look like? So h of x is going to be producing log n bits. The value of h here is an element from 1 to n, so you need log n bits to describe it. And the way we'll describe it is as a concatenation of log n simpler functions. So h1 of x will give us half of the bits. h2 of x will give us half of the remaining bits, and so on, up to h log n. So h log n, which will give us the remaining bits. In fact, in our analysis, we don't use half of the bits, but any constant smaller than that would do. Okay. What about the independence? So hi is going to be 2 to the I wise 1 over n dependent. So the length of the output shrinks, but the level of independence increases. And this means that we have log n functions, and with these, if we use these functions, we get that each one of them requires a log n evaluation. So altogether we get log n squared evaluation time. And anyway, we get log n times log n. Okay.
Are you using h1 recursively?
What do you mean recursive?
So h1 is also defined like h of x?
No, h1 is just
It's just the one
But
time?
just two-wise independence.
But
Two-wise
how
almost.
larger range?
So hi is a function still from n cubed,
Di plus 1, or?
from n cubed to n to the 1 over 2 to the I, or something like this. And h is just the concatenation of h1 concatenated with h2 concatenated up to h log n.
Okay, so that's representing the concatenation, but also the description, or?
Yeah. So no. So this is the description of h is just the description of h1 h2 up to h log n. So this represents here the evaluation. When you evaluate h on x, you I'm looking at how optimistic about h of x, then
The first half of the bit.
the first half of the bits are just the application of h1 on x. The second, the half of the remaining is h2 applied to x.
But just description of the last one will be log n times log n, right? The last
The last one, yeah, if it's log n wise independence, it will be log n times log n, but actually it can also be log n. It can be log n over log n wise independence.
So you can think of h1 as you're putting your n elements into square root of n buckets pairwise independently, and then h2 works on each bucket.
Right, right. So, okay, so what I won't show you, but I'll sketch, is the analysis. The analysis uses, again, as I promised, a very, very elementary property of k-wise independence, and the property is that an extension of Chebyshev. So it's that k-wise independence are sufficient for k moment inequalities. And the argument that we'll have is, so here we have the set S, and the set S is going to be hashed. And you can think about kind of a tree structure of its hashing. So it's going to be hashed by h1 to square root of n subsets, depending on the value of h1 here, right? So it will be hashed to s of 0 up to s of 1, and we will argue that all of these sets are of the right size. Namely, each one of these sets is supposed to be roughly square root of n. Right. And then recursively, we'll try to argue that h2 splits each one of these sets to the fourth root of n subsets that are roughly of size fourth root. And the reason it works, which I won't expand, but it's very, very simple, is that at each point, so why would pairwise independence be sufficient for the beginning? It won't be very good if we do everything with pairwise independence, but for the beginning, or 4-wise independence, 10-wise independence should be good enough, because we're talking about large sets. So we're talking about the deviation of a large set from its expectation. We have lots of experiments. We're throwing the first ball, the second ball, the third ball, and therefore in our moment, in our k moment inequality, we're getting a lot of advantage just by the big numbers that we're using. Therefore, we don't need large independence. On the other hand, for smaller and smaller sets, we do need more independence because the sets are smaller. So eventually we'll get to sets of size log n. We'll just try to be completely uniform on them. Or sets of size log n over log n will be completely uniform on them, and we'll be okay.
I'm a little bit confused. I mean, the way you described that each HI has the same domain n cubed.
Right.
So you're not reducing the domain.
I'm not reducing the domain, but the value of, so I can define, so SZ for the first set can be defined to be age 1 minus 1 of Z intersection with S. So I'm adding more and more conditions on the set. So here, if I want to be here, then I want to be in the intersection of age minus 1 of 0, but also age intersection with age 2 minus 1 of 0. Each one of these conditions will split our set further.
But But then why not just to use log? I mean, you're not getting it. You just use log n, log n, y state dependence all the way. Why do you need to use different levels? I mean,
To be
No.
you don't save on the seed length.
This
All
is
the
not.
efficiency.
This is pairwise. I mean, this is not more than pairwise. The entire thing is not more than pairwise independent, because the first bits are just pairwise independent.
I see. So this is for evaluation time because on the seed lengths you're not saving, right? You're not
Yeah.
saving.
No, it's-
Yeah.
Because
Maybe you should say what's the seed length if you want K-wise independence mapping from
Right,
n
okay.
to that.
Okay, so let's do that.
oh, maybe that's what I see. What you're saying is output is smaller. It's actually smaller. I see. So
The K equals multiplies log of the output length, no?
I see.
Log
So
of the
okay.
input
No,
length.
no, okay. Yeah, I forgot about it. Good.
Actually, all of these HIs are just one function. So let's see that. So the function HI, yeah, I'm trying to hurry up, so I'm kind of cutting corners, and it's never a good idea. So let's think about our function HI. And think about it as a long bit string, right? So HI of 0, HI of 1, and so on. So HI of n cubed. Now the length of each one of these blocks is log n over 2 to the I. Right? These blocks, the outputs of HI have shrunk by constant factor each time. The level of independence has doubled each time. So what I want is that if I take 2 to the I such blocks, and I only look at them, they look uniform. How many bits should be independent of each other? I need order log n bits to be independent of each other, right? And that is maintained by the construction. So what actually it means is that it's enough for me to take here, for all of these functions, bit strings. So when I view it as bit strings that are log n wise 1 over n dependent, or alternatively I can use 1 over n or 1 over poly n biased sequences for those who know what it is. Describing something like this only requires order log n bits. So description is order log n. By our work, so traditional things also requires evaluation to be logarithmic. Our work shows how to do it much more efficiently by log n word operations. Okay. So, in conclusion, let me try to see what kind of I'll skip what we know, and if you want, you can talk with me, but let me say some of the open problems that we...
Omer? Question. So you need fresh randomness for each of the HIs.
Right.
Is there a way of generating H2 from H1 using the...
That's a good question. So yeah, so reducing, definitely an open problem is just getting description order of log n. And we don't know if it's possible or not. I don't know. I mean, you're suggesting something, recycling the HIs would be a good way of doing it. We don't know if it works. I want to say that this is interesting. From my perspective, this is possibly one of the simplest questions about small space computation that you can ask. This is one of the simplest settings. So at least in this setting, we can think about it as, we can try to get the best generators I won't immediately describe why it's small space computation. And our work so far has provided us with generators. Starting with that, you do get, there's lots of other objects that are interesting that you can de-randomize, and I think that Thomas Stinke is going to talk about it. But definitely we de-randomize read one CNFs with this object that we called mild restriction generator. As far as we know, could de-randomize RL completely. And potentially it's one of the interesting directions towards that. So that's one kind of question here. Let me say kind of what's the, just tell you something about the kind of problems that we get from the cuckoo hashing and the kind of problem that we care about. So the problems that we get has to do with kind of pseudo-random graphs that we, an object that we really like, but a different kind of pseudo-random graphs. So think about a domain of size n. And now think of the graph you get by mapping a set S with H and G to this domain. We can look at this mapping as a graph. How can we do it? We can look for every x in S, we can look of this edge, h of x and g of x. Right? So every element is mapped to two places, and we can think about it as an edge. So mapping a set of size n gives us n edges in this graph, and potentially the graph, if the graph is a little bit larger than n, what you get is a graph in a subcritical setting of parameters. So in particular, what you'll have is that every connected component will be at most logarithmic. And in addition, every connected component will be pretty sparse. And what we show in that work over there is that our functions preserve these properties. So this is a way to get a pseudo-random graph with this property, that all connected components are small and sparse. But we can also ask this in the setting, let's say, when it's n over 10, or even smaller. So in the domain where connected components can be large. And that's the domain for some of the more advanced cuckoo hashing kind of applications. And here, even log n-wise independence doesn't provide what we need. So we will have here connected components that are large, but we want to say that they are still relatively sparse. So for example, for every set of vertices, for every connected component where this is the set of vertices, the number of edges is at most some constant times v.
Are they large diameter, these large components?
They will. So if it's a random graph, then probably not. Perhaps it's something to use. No. So no, of course not, because they'll be expanding as well. But this is the kind of analysis that's needed to what's known as blocked cuckoo hashing, which is a very nice object. Here, not only our functions don't work, not even log n-wise independence work, and this is a very clean kind of problem that would be interesting to see. So the reason log n-wise, I'll conclude with that, the reason log n-wise independence works in the subcritical case, but not here, is that in the subcritical case, at least intuitively, all connected components are small, so we only care about events on log n kind of vertices, whereas here, the connected component is large. And we just, we somehow need to analyze it nevertheless. Okay, So lots of other things to tell you. If you want, come and ask me. Thank you.
Are there any questions? Okay. If not, then there is a pile of photocopies of our list of lunch places if you haven't picked one up. Enjoy your break. It looks sunny. We'll meet back here at 2 p.m. For the afternoon session. So let's thank Omer again.